Okay, good day, everyone. This is Professor Grenfell's Math 12 Statistics class. We are still lecturing in Chapter 9, Section 4, talking about the difference in proportions. And as it says, we're going to do a follow-up to the previous example, example 9-10, and we're going to do example 9-11 as well. Both of these are pertaining to confidence intervals for difference in proportions for two populations. And just put difference of p's. No, let's say that. Okay. And our first example is going to be one that I made up completely on my own. No, I'm just doing the same thing as example 9-11. This is to create a confidence interval for the data in 9-10. And in doing this one, we're going to kind of tweak it a little bit, but it's fine because all of this is inferential statistics anyway, and so we have a little bit of leeway in terms of answering the research question. Remember, when they don't tell us significance level to set, we just set it ourselves. So here, even though the data or the question, the test that we performed in 9-10 was a single tail test, here we're going to examine a confidence interval that is pertinent to this same research question anyway. And this is a great opportunity to talk about confidence intervals for a difference in proportions. So I'll set it up the same way that I always do. I'm going to say that the true difference in population proportions, so these are without any adornments, no symbols attached to the p's, just the subscripts. P subscript 1 is the population proportion for the first population. P subscript 2 the population proportion for the second population. And to get this difference, this confidence interval, for this difference, we just take the difference in the samples and, whatever that difference is, that's the part that's in the middle, and then we do plus or minus our margin of error. And now the book will throw the whole formula right at you all at once, but I like to break it down like this because then, just remember two smaller pieces and put them together. So here, the error, the margin of error, is the critical z-value times our standard error for the distribution. And here, it's a little bit different than we used in the hypothesis test. It's probably more similar to what I would have envisioned using anyway. So we have P1 hat times Q1 hat, all divided by n subscript 1 plus P2 hat times Q2 hat, all divided by n subscript 2. And that's, of course, all underneath the square root. So those are our principal tools here. So we're going to go back to the data that we had in example 9-10. And let's see, 9-10 info. I see n subscript 1 is 50. P1 hat we were given was 0.16. Notice here we don't need to use x subscript 1 because we're not computing a weighted average. So all we really need to talk about is what is q hat. What is the complement of this one? So that's 0.84. All right. Then for the second population, this was the car thefts. The first one was the burglaries. We had 50 car thefts. The arrest rate for this sample, so that would be P2 hat, that was 12%. And in the previous problem, in example 10, we needed the the number, the actual number of arrests that they made. But in this case, we don't. We just need the complement of this probability here. So that is what? 0.88. And so that's the basic info for 9-10. And so here I'm going to say, what is the confidence level that we need? What is the confidence level alpha corresponding to the significance level alpha that we looked at in our hypothesis test? So here I'm going to say alpha over 2 is 0.10. And that was because in the previous example, we were doing alpha equals 0.10, but it was a single-tailed test. So here I'm saying not alpha. Alpha is not 0.10. Alpha divided in half is 0.10. So actually, this would be not the 90% confidence interval. This would actually be an 80% confidence interval. I'll draw you a picture in just one second, but accordingly, the critical Z subscript alpha over 2, if alpha over 2 is 0.10, then G subscript alpha over 2 is 1.28. So in example 9-10, when we did our hypothesis test, the critical region was over here, and the area was 0.10. And so we came up with the critical Z value, 1.28. And so in this case, when we're doing our confidence interval, we want to have an interval. So we want to have two endpoints. We don't just want it to have a right side and continue indefinitely to the left. So we're basically going to just say, okay, look, we'll bound it off on the other side. So this area over here is another 0.10. So notice that makes this only an 80% confidence interval. But that's the deal nonetheless. So that our work for this confidence interval problem mimics or kind of answers the same question that the previous problem did. So let's just keep on going. Bam. So all of that materialized right there. So the margin of error, again, was the formula above. I didn't waste the opportunity to try to write it down again. So there's that. And then we just substitute in all of the values, and we get out our margin of error is, margin of error is 0.0887. And then our difference in these population proportions, okay, I just write it as our difference, the sample difference, plus or minus the margin of error. So the sample difference is 4%, and 16% for the burglaries, 12% for the car thefts. So 4% plus or minus 0.0887. And so when we add them together, that gives us 0.1287. When we subtract 0.04 minus 0.0887, we get negative 0.487. I think I said that wrong, but it's written correctly. And this would be the population difference. Okay, so P1 minus P2. Notice that 0 is somewhere in here. So notice here, we have no idea what these true proportions are for these two populations. All of the burglaries and what is the grand total all-inclusive arrest rate for all burglaries. We have no way of knowing that but by doing tests. And so what we are saying here is whatever these population proportions are, we have no idea, but the difference in the population proportion for burglaries versus the arrest rate for car thefts is anywhere between negative 4.87% and positive 12.87%. Okay, so that means one could be higher than the other, or it could be the other way around. Since 0 is in here, that means that it's close. The difference is close enough to 0 that there is no discernible difference. That's basically what we would say about that. Okay, so example 9-11, find the 95% confidence interval for the difference of proportions for the data in example 9-9. So that was the one on small nursing homes versus large nursing homes and the proportion with a low vaccination rate. Okay, so here we had copied down the data from the previous one. Here it was important to get these actual percentages or these proportions themselves. So I don't care about the raw numbers as we did in the previous case. I need the decimal value. So doing these divisions, this is 0.35, so therefore Q2 hat is 0.65. The complement is 0.65. Let's actually do the complements in purple, just because. All right, and so if the probability for P2 is 0.71, then the complement of that would be 0.29. And so, yes, that is all we need to construct our margin of error. So we need to find a critical Z value, and then here it's going to be P1 hat times Q1 hat, all divided by N subscript 1, plus P2 hat Q2 hats, all divided by N2, and all of that, all underneath the square root, and yeah, all of that. Yes, so we substitute everything into its correct place and work this out. So 1.96 times the square root of the whole entire quantity, 0.35 times 0.65 divided by 34, plus 0.71 times 0.29 divided by 24, works out as 0.2422. So there is our margin of error. So our confidence interval is found by saying our true proportion, true difference of the proportions, P1 minus P2, is the sample difference, P1 hat minus P2 hat, plus or minus our margin of error. And so as we had found previously, this is 0.35 minus 0.71. That works out as negative 0.36. And then plus or minus 0.2422. And so this translates into our 95% confidence interval of negative 0.6022 all the way up to negative 0.1178 for the true difference in these two population proportions, so P1 minus P2. All right. So again, we have no idea. We have no idea what the true vaccination rate is for the small nursing homes, or what the proportion of, it's not the vaccination rates, the proportion of small and large nursing homes with this low-ish vaccination rate. Okay, so we found that if you take the proportion that are vaccinated at this low rate out of the small nursing homes, and you compare that to the proportion for large nursing homes, that is going to be anywhere between negative 60% and negative 11, 12-ish percent. Okay? So that means what? That means that when we subtract this one here minus this one, we get a negative number. That means the orange one's bigger, right? So the large nursing homes appear to have this higher, this higher rate of vaccination. I'm sorry, I'm saying that wrong. They have a higher proportion that have this lowish vaccination rate. Yeah, that's what I want to say. And that difference is anywhere between negative 60% and negative 12-ish percent. So notice that doesn't include zero. It's always negative. That means no matter what the actual difference is, it's negative. That means that this proportion truly is lower than this proportion here. And that's what we showed, or that's the same conclusion that we came to when we performed our hypothesis test. And so, again, we see there's this inherent connection between hypothesis testing and the formation of a confidence interval. It is essentially just gives us a stricter way to logically interpret these results in order to answer a more pointed question when we do a hypothesis test. Well, at least that's how I see it. So until the next video, we'll open up the next section.